Both. Okay. All right, so stereochemistry of halogenations, right, is something that we do have to account for. If we were to go through and do this radical bromination, you know that since bromination is selective, it's going to pop itself onto one of the middle carbons. Right? Now, you might notice, though, after the fact, that we've created a new stereogenic center. All right, so just like we always have to do whenever we're doing a reaction and we make a stereogenic center, we've got to determine what's going to happen as far as the stereochemistry. Right? Always look at the mechanisms, right? Look at the carbon that's getting attacked and basically ask yourself, what's the hybridization of this carbon as it is being attacked? Right? I'm not writing the whole mechanism up here, but you go through it, you know that at some point you're going to make that carbon radical. That's the most stable radical that you can go through. Since bromination is selective, that's the one to use, right? And then once you form this, it reacts with a Br radical from Br2 in order to get your final product. Right? The question is, where can this come from? Can it come from front side, back side, or either? All right, well, let's look at the hybridization. What's the hybridization of that carbon right there? sp, sp2, sp3. Some heretofore unknown hybrid orbital. It's not going to be that. Well, how do you figure out the hybridization? What do we count? Quiet. Figure fewer people, maybe you're chattier. Not a correlation. We're starting to get a crowd now. Those of you who just came in the last few minutes, like we had like 8 people here at the beginning of class. So starting to feel a little bit more normal. No, what is the hybridization of that indicated carbon? What's that? sp2. Well, let's take a look at it. Remember, we count the number of groups. Groups include other bonded atoms and unshared pairs, right? We have an H here, of course, that we haven't drawn across the skeletal structure. So we have 1, 2, 3 bonded atoms right there. What people get confused about sometimes is, how do you treat this? Do you treat that as a group? Do you not? Well, if you go by the definition, it should be an unshared pair of electrons, right? Is that an unshared pair? No, that's an unshared single electron. So this does not count as a group. So, sir, you are correct. This is sp2 hybridized. How do you think that's going to impact the stereochemistry? It's sp2 hybridized. What's the geometry around it? I accomplished nothing else from organic chemistry. I'll make sure you know hybridizations and geometry. What's that? Trigonal planar, flat as a sheet of paper. So what does that mean about attack? You can attack from both sides. So yes, that means you would get a racemic mix. You get a racemic. And that's something that you can remember going forward, right? If over the course of a free radical halogenation, you create a new stereogenic center, that is going to result in a racemic mix, pair of enantiomers. Always and forever. All right, so it's just something kind of good to remember as you're doing these syntheses and trying to produce stereotypes. All right, does that make sense? Are there any questions about that? All right. One nice thing about, kind of cool thing about organic food, I think, is that we're getting to some more complex stuff, and we can see more and more applications of things in, you know, the so-called real world. We can see an example of how free radical halogenation and free radical reactions in general have had big impacts on environmental chemistry, right? I'm assuming you guys have probably heard of the ozone layer before, right? Right, what's the ozone layer important for? Why do we care about it? Not to control heat so much, but you're in the ballpark. Yeah.
Is it
Yeah. It basically acts for us as sort of a shield for harmful ultraviolet radiation from the sun, right? Basically, you know, the ozone layer takes one for the team there as far as absorbing those harmful UV rays so we don't have to, right? Now, back in probably, I don't know, right around the early 1980s or so, there started to be concern because there was development of a hole in the ozone layer. Now, the hole is actually not anything new. It's always been there, but it usually was pretty small. But there was really a lot of concern because people could see that the hole was growing bigger and sort of at an alarming rate. Have you guys, I know this is like really far back now, but have you guys discussed the hole in ozone layer before in other situations, contexts? Right? Yeah, right. Generally located, the hole is generally located over Antarctica. And it's definitely bad news, right? Though we have a bigger hole in the ozone layer, that means more harmful UV rays can get in. We can absorb them. That leads to a lot of concerns with regard to skin conditions and eventually skin cancers, right? Do y'all know what was largely responsible for the growth of this hole? Who said that? CFCs? Yes, CFCs. Who in here knows what the heck a CFC is or has heard of one before? You've heard of them before? Anybody know what they are? Chlorofluorocarbons. Excellent. Yeah. So, yeah, CFC stands for chlorofluorocarbons. And there are lots of different types of these. Here's a really simple example of one. Something like this, for example of a chlorofluorocarbon. CFCs were used quite a bit in the 1980s and 1970s. I'm not really sure how far back their use goes, but they were used in a lot of consumer products. Anybody know what kind of consumer products they were used in? More testing your history knowledge here, I think, than your chemical knowledge. Aerosols, yeah. So, you ever seen photos? Gosh, I guess by now probably of your parents, maybe, or relatives or something. See photos of people back from the early 1980s? See their hair? What does their hair look like? Yeah, it's like a big giant helmet, right? One of the biggest users of CFCs was, my grammar is really bad here. CFCs were used quite a bit in hairsprays, various other types of aerosols as well. That's kind of a funny one though because of the 1980s scare and all, but it's a good example. Aerosols were used quite a bit back then, and almost all of them employed the use of CFCs. CFCs were basically used as a propellant. You know how you squeeze the hairspray button and the spray comes out? Well, it's not the hairspray. If you just put the stuff that sticks your hair into place, like in the can, and press the button, it's not going to do anything. You have to have a propellant, and this is basically sort of a pressurized gas that's put in the can. So when you hit the button, the pressurized gas can escape, and it just sort of carries the hairspray or whatever, or the air freshener or whatever else with it. Okay. So CFCs are really, really good propellants. So that's why they were used so much. All right. Unfortunately, it was observed that later on that these were having very negative effects chemically on ozone. All right. Let me show you what happens normally with the ozone layer. All right. All right, so this is normal without the interference of CFCs. All right, you have ozone sitting there, and as you guys know, ozone is O3. And we said that it can act to absorb ultraviolet radiation. It does. Now, when it absorbs ultraviolet radiation, it actually decomposes. It breaks down. Forms O2, which is molecular oxygen, and also a radical form of oxygen, specifically a diradical, since it's got two individual radicals. Right, so you may think, okay, that's bad. We need the ozone. However, that diradical that you just made, and that oxygen, they can react immediately and reform ozone, plus they give off a little bit of heat. This is a cycle. This is the ozone cycle. So we constantly deplete ozone, but we constantly reform it. So that's good. Really good. Constant source of protection from these ultraviolet rays. All right. Now, let's take a look at what happens when we include CFCs into the mix. CFCs, when you release them from like a can or whatever, they travel, they ascend into the stratosphere, right? Once they get into the stratosphere, they can then interact with ultraviolet light or heat or whatever, right? I'm just sort of going to take that initial CFC I showed you and write it like that just to show the mechanism. All right, so what can happen is when this is hit by UV light, if it's hit by heat or another energy source, it can cause this bond to break. That's one of those CCl bonds. So it's going to create a carbon radical, which honestly we don't care about. That's not a harmful species right there. That's not going to do anything. But what is bad is this little guy right there, chlorine radical. This is going to be what targets your ozone. Once you form that chlorine radical, it can break apart ozone forms a CLO radical and molecular oxygen, O2. So that's bad. We just broke apart some ozone. Here's what's even worse, though. That CLO radical that you just formed can react with oxygen diradical that might be in the area from all this up here. That forms O2 and more Cl radical. This is a propagation. Remember we talked about initiation, propagation, termination? This is a propagation because what can this Cl radical then do? It can find some more ozone, break it apart, right? This, again, this is a cycle. Unlike the top one, though, which sees ozone being constantly depleted and destroyed, this one, you don't see any more ozone being made in any of these reactions, right? So ozone is being constantly depleted and not replenished, and you're constantly making more of the species that destroys ozone. So see how that's not such a good thing? Yeah, that's really bad. So like I said, these were used quite a bit. These CFCs were used quite a bit for various applications, not even just aerosols. They're actually still used for things. Refrigerants, air conditioning species. Freon, I think, is a CFC, excuse me. But in response to this, there were a lot of laws enacted worldwide to either restrict or ban the use of CFCs industrially, right? And I've got an interesting video to show you here. So first I'm gonna put it on the projector. And then for you Zoomers out there, I'll share my screen. One second. All right, so this is an interesting video on YouTube. And you can find a few of these if you dig around. NASA has been monitoring the ozone hole for quite a long time now, since the early 1980s. And so every year they use thermal imaging to sort of monitor this. And so you can actually sort of get a visual representation of the ozone hole. In fact, in this still image right here, you see this blue part right over here? Oh, that's right, because I have the page not big enough. Fix the lighting. Now you can probably see a little better. All right, so you see this blue part right over here? That's the ozone hole. All right, and you can actually see how it sort of changes with this time-lapse photography, time-lapse video. One thing that's kind of interesting, within the course of the year, it changes. It's actually kind of a bit seasonal. In certain parts of the year, it's worse than others. I can't remember which part. I'll probably find out here. But also, you can kind of see how the ozone hole in general has changed appearance over a course of years. Right? So I'm not going to play the whole 3 minutes of this, but I'll play part of it. All right. So you see, we're in the early 1980s, and you can see that blue spot's getting pretty big, right? If you go to the same corresponding part of the year, it's really, really growing and getting larger. So you see, all through the 80s, very problematic. That's the price we paid for our mall hair. I didn't have mall hair, but yeah. Although I will confess, at one point for a brief period of time, I did have a curly mullet. So yeah, just imagine that. All right, so anyway, still in the 1990s, pretty big. All right, I'm going to fast forward a little bit here. I really probably shouldn't have said that. But, well, all right, let's see. This is like 2004. And you may notice that it's still substantial, but it's not quite as big as it was in like the mid 1980s. It is, in fact, for a while now, it has been slowly shrinking, which is good, right? The reason it's been shrinking is, you guys can look at that on your own. The reason it's been shrinking is because the use of CFCs has been dramatically curtailed by a bunch of industrial regulations. So the ozone layer is making a comeback. Trying to get my zoomers back on. There we go. So there's other things that we can use now instead of CFCs. And some of them are really similar derivatives. I'll get this right. HFCs, for instance, are commonly used now. Basically, chlorines are replaced by H's. So, yeah. Here's one example, right? And there's several others. You have HCFCs, where maybe one or two of the chlorines has been replaced, right? Each of these will form radicals as well, but the radicals that are formed with these don't actually float up to the stratosphere. They get destroyed by ambient OH radicals before they ever get up there. By the way, there's free radicals floating around all around us right now. Yeah, can you see them? For you extra paranoid people out there, the radicals, the OH radicals are floating around. They're real common. Nothing to worry about. In fact, they're helpful. If you look on a bottle of like hairspray or bug spray or whatever, which I'm sure somebody probably happens to have right now. Yeah. No, didn't figure. You might see that within the bottle, it might say something like the ingredient list. It might say something like butane or hexane or something like that. An alkane. Alkanes are really good at propellants as well once you pressurize them. One nice thing about CFCs, that was one good property, one reason they were really good propellants is that they were largely non-flammable. I don't know if I should ask, have you ever made the hairspray flamethrower? Where, yes, like a bunch of you before I even got the sentence out, you're going, oh yeah, I totally have done that before. That's because like these alkanes they put in as propellants, they're very flammable, right? So you can go, be Rambo and do that. Couldn't do that with CFCs. So that's kind of a trade-off that we've had to make. But we just have to now rely on hopefully the fact that, sorry, I'm trying to fix my Zoom. Rely on the fact that people are not going to be stupid enough to set themselves on fire. Right? So I'm not going to ask who's got something. All right. So pretty interesting application of radical chemistry in an environmental setting. So, put a little free plug in here for Helms's environmental chemistry class. You ever take environmental chemistry? Perhaps we'll talk some more. All right, so let's keep on talking about halogenation, right? There's another type of bromination we can look at that falls under the category of, sort of brominating alkane groups, but it's at a very specific spot. And that's at the allyl position, right? We talked about this, a time or two before, right? We've talked about allyl radicals, and we know that they're more stable. They're easier to form than non-allylic radicals, right? So for bromination purposes, you'd think since bromination is selective, yeah, it's going to want to target an allyl radical whenever possible, right? However, not quite as simple as you might think. Let's say you had this. This is cyclohexene. Right? And let's say we wanted to do an allylic bromination. That means we want to put a BR right there. All right? Well, based off of what we talked about, what would you expect we put as the reagents? What have we been using? What's that? Heat's one of them, okay. And what else? BR2. So it stands to reason, okay, if bromination is selective, then yeah, it's definitely going to target this carbon if you do this. However, that is not what you get if you use this setup. There's something else that happens. What is it? You guys have already learned about this. You get a competing reaction that is preferable to that. Competing reaction that is not necessarily from this chapter. That was covered on the test a day or two ago that you may have already flushed out of your minds. Halogenation of an alkene, yeah. We've already learned that if you have an alkene, you add Br2 to it, doesn't matter if you have heat or not. You're going to get this. You're going to get an addition to the alkene group, preferably over a radical substitution. So if you want to make this right here, you can't add Br2 in heat. That's sad. However, there is a way around this. All right, so what we want to do is we want to keep that double bond intact and still allow a radical process to go through at the allyl position. To do this, we're going to use a new molecule, a new reagent. NBS. I'll explain what that is in just a minute. NBS in conjunction with an energy source of some sort, UV light or heat. All right? All right, so let me explain what NBS is. NBS stands for N-bromosuccinimide. And here's the structure of it. It's definitely kind of different looking. But basically what this does, NBS gives us a source of bromine. It gives us a source of bromine that's not Br2, right? We can take advantage of this in order to sort of work around that double bond. Right? So just like any of the other radical processes, we have initiation, propagation, and termination. Right? Let's take a look at initiation. Initiation, we have to form radicals, right? So you're going to do this off of NBS. Let's just say we have some heat. This is going to cause that nitrogen to bromine bond to break apart. Split right down the middle. And you're going to form two radicals. All right, you're going to form a nitrogen radical, which honestly we don't care about anymore. This does nothing else. The more interesting one is going to be that Br radical. That's going to be where we make our money. Yeah. Then we get into propagation, right? When we get into propagation, we're going to have our cyclohexene, and I'm going to draw that H out there so you can see what happens mechanistically. You're going to have your Br radical, right? That Br radical is going to pluck off an H radical from your allylic carbon. And so you end up making some HBr. And more importantly, you make an allyl radical. HBr is just a waste product. All right, y'all with me so far? All right. Limited on space, so I'm going to erase some of this. And I'm going to continue propagation because we're not done with propagation. All right, so there's a second step in propagation. That allyl radical that you just formed is going to react with Br2. Now, if you're paying attention, you may have a question here. What would the logical question be? Where the hell did the Br2 come from? We're going to explain that in just a minute. But just take comfort in the fact that it's there, right? This Br2 is going to split up. One of the Br radicals will combine with the carbon radical. The other Br radical will separate on its own. So boom, you get the product here. And again, if you're paying attention, you might notice that we have a stereogenic center. So this will exist as a racemate. And you also get more Br radical. This is a propagation, so that means that Br radical can still be active. You can restart propagation, and it goes onward and onward and onward. Okay? That make sense? All right, now let me answer the question, where did you get Br from? Br2 from, excuse me. Well, you create Br2 as part of terminations. Remember, terminations can involve coupling of radicals, coupling of any two radicals. So, you know, you might see, you could even see two of these link up to make sort of this weird organic product that would be sort of a side product, right? One of the terminations that can occur is a Br radical combining with a Br radical to make Br2. So it's a little trippy to think about here. Basically what happens is you take advantage of a termination product to fuel propagation. Does that make sense? But yeah, that's where it comes from. So bottom line, to do this, you gotta have Br2, but number one, you don't want a whole lot of it, right? This just forms a little bit at a time. right? You don't have like this big batch of Br2 initially, so you only have a little bit at a time. And number two, it doesn't form until you already have carbon radicals present, right? Br2 would rather react with a carbon-carbon double bond than a CH bond over here, but it would rather react with a carbon radical that's already formed than your double bond, right? So it's a really elegant, that's a word chemists use when something's kind of complicated. We like to call it elegant, because it sounds better. A really elegant solution to the competing reaction problem. Okay? Does that make sense? Are there any questions so far? All right. Let's do another one here. It can get a little bit more complicated. All right, this one's going to be a little bit different from the last one. I'm going to do this. Okay. And I'll go through the mechanism of this one, the whole mechanism of this one with you. So initiation, you have NBS. By the way, sometimes I'm lazy because I don't want to write the whole structure, and I'll just represent NBS like that. If you want to do that, that's fine as well. First you have to make the Br radical. And then your alkene interacts with the Br radical. So what does the radical do here? Look back if you need to. It's going to break off an allylic H. Yep. We have an allylic position right over here. So H radical is going to bond with that. And you're going to form a carbon radical. All right. And then what did we say happens? Nothing's new, by the way, right now. You can go strictly off the last example of the Br2 that you got from termination can come in. And that can make a product as well as more Br radical. Nothing's changed so far. Okay. So far, so good? All right. I'm going to redraw this carbon radical because something is possible here that wasn't possible before. All right. We're going to use the dreaded R word, resonance. Oh, yes, I know, right? Yeah, we can have resonance structures with radicals, just like we did with ionic species, right? You have extra electrons over here that are able to move around. It is entirely possible for this pi bond split, like that, one electron from here meeting up with this electron sort of in the middle to make a pair. And this electron hanging back on that carbon. And that does happen. This is a resonance structure. Right? This radical, we said allo radicals were stabilized by resonance. Here's an example. And so the resonance structure for this one looks like this. Now this happened in the last example as well. It just so happened that both resonance structures were basically identical to each other. So there wasn't, a different structure to it. Whereas this one you can note is notably different. Y'all see where we got that from? Does that make sense? So each one of your resonance structures could potentially react with Br. And so this means that you can have a mixture of organic products. That happens fairly regularly. That probably happens more often than not with these allylic brominations. The only time it doesn't give you multiple products is when both resonance structures are basically the same. Okay. Does that make sense? Are there any questions so far? All right, let's try another one. Please UV light for fun on this one. All right, now this one is more complicated still, even over the last one. Just from looking at our setup, can anybody tell me why this one's a little bit more complex? Yeah, in each of the first two examples I gave you, there was only one type of allylic hydrogen attached, right? But guess what? We got two of them here. So we got to make a bit of a choice. We have to decide, is it going to choose one over the other? Is it going to choose both? What do we think? Well, let me ask you guys. What do you think? You guys have the tools to figure this out. Would you, let's see, I'll even kind of nudge you along here. Would you attack, oops, not that. Would you attack this allylic position? Make that radical? Would you attack this allylic position to make this radical? Would you do both? What do you think? You boil it down, it's only three possible answers, right? Left, right, or both. Unless I just threw ether in there as a swerve. But I'm not going to do that. Remember, ask yourself questions. If I were you, I'm looking at this, I might ask myself, okay, what type of radicals did I just possibly make? What type of radicals on the left-hand side? What's that? I think I heard it, but I'm not sure. It is a not only primary, but primary allylic. Yeah, primary allylic on the left. What type is on the right? Tertiary allylic. So then you ask yourself, do both of those radicals have an equal chance of being formed? Is one preferred over the other? What do you think? The right one. Yeah, remember, bromination is selective. It goes through the most stable radical that it can initially form. So you have a choice here. However, because this one is the most stable one, that's the one that initially forms. Does that make sense? Yeah. So this is a case where we don't. You're probably used to me saying, well, you got to do it at every position. No. Here you have to just be able to figure out which is the more stable. From there on out, it's pretty simple. It's going to follow the mechanism as I've outlined in previous examples. I'm not going to go through it all. But if we are sort of fast forwarding with this one, you could put a BR right there, right? What's the other thing that could happen? That we just looked at in the previous example. Yeah, you still have to worry about resonance, right? You can form a resonance structure. And I realize the resonance radical is not as stable as the initial one, but it does still happen, it does still form. So you would also get that as well. Would you get them in equal amounts? Probably not. You'd probably get the top one in higher amounts, but they would both still be there. All right. That makes sense. Any questions? Have we covered enough for today? Or do you thirst for more knowledge in the minute or two that I have left? I see somebody going, yeah. Watch out, you're going to get a bunch of stuff thrown at you if you're not good. All right, I am going to stop there. We will have a quiz on Monday. Radical chapter up to this point. All right. I also have, I finally remembered to bring the first two quizzes here. So if you want to pick them up. They're in two different stacks, so you'll have to wait for your name to be called twice to get them. Let's see, Riley. I realize there might be a lot of people not here. What's that? Oh, sorry. Sadie, are you here? Okay. Aiden. Tori is not here, I don't think. Oh, yeah, Tori. Oh, you are here. Okay, yeah, sorry. Tori. It's really hard to figure this out when everybody's in masks. So, sorry. Sam, are you here? Carissa. Josh. Matt Strucker. Nick. Meryl. Ray. Christia. Emily Dufek. Did I say your name right? I do it? Okay. I couldn't remember if it was that or nothing. See how many? Emily Kluckfelter. Nikki, I think, is off on softball. Katie. Sabrina. Hazel. Matt Bennett's not here. Andres not here. All right, Josh again. Marissa Hernandez. Zan's not here.